We are nearly at the end. We have finally made it to the applications of recurrence relations. So, how can we apply recurrence relations? First off, counting. It's half of what they do. But perhaps less obviously is algorithm design. They help us divide and conquer. They help us figure out complexity. They help us with dynamic programming. So, here's a little bit of a case study. But before that, a quick break for me to advertise while I blow my nose. With that done with, our case study: bit strings without consecutive zeros. So, let's say that A of n. I've gotten so used to using latex that I write an underscore when I'm using pencils. Not good. Is the number of strings that satisfy the number of satisfactory strings. Good. I'm just going to use a check stirs. Good stirs. Check mark stirs. These are satisfactory strings, so it can't be of length n. Satisfactory strings of length n. So, we can pretty quickly find the first set of those, right? A of 1 is going to be 2 for 1 and 0. A of 2 is going to be 3 for 1, 0, 0, 1, 1, 1. A of 3, we're not going to deal with A of 3, too big. But you might notice a few things. First and foremost, you can use any string in A1 to make a string in A2. Like, consider 1, 0, right? How would we bring that into A3? We'd put a 1 on the end. 01. How would we bring that into A3? We would either put a 0 at the end or a 1 at the end. 1, 1, 1. We can either put a 0 at the end or a 1 at the end. The real question comes when we're looking at these is, does this include anything that isn't in here? Like, that isn't built from there? And the answer is no. And if we continue thinking about that, we just have 1, 1 here, a 1 here, and a 1 here. If it ends in a 1, that means that there will be 2 of it. So you'll in the next one, or it will have 2 offspring. And if it ends in a 0, it will only have 1 offspring. What does this mean? This means that however many there are in the original list, the next list will have 5, or not 5, sorry, will have the length of n will have n minus 1, a of n minus 1 odds, right? Odd options. That's just guaranteed because there are no new things. Like everything that was in here uh, will be in the next one. In that, though the starting characters will just be these two, and the starting characters of these will be the only starting characters you see in the next one, right? And starting characters I'm defining as size of the characters or size of n minus 1, essentially. Did not have time to commercial for that nose blowing. So that means we just have to figure out how many ending in 0 there will be. And this is actually very doable, because let's get rid of some of these markings. If we look at AF2, right, from AF2 to AF3, you might notice something. All of these and have an offspring that has a 1 at the end, but only the ones that end in 1 have an offspring with a 0, which means that the amount of offspring that this one will have that end in zeros will be equal to the amount of offspring that this one has total. Why is that? That's not true. Let me rethink that really quick. I mean to say that the amount of offspring that this one will have that end in 0 will be equal to the amount of offspring that this one had total. Or will be equal to the odd offspring of the previous one, specifically. Because the odd offspring are the only ones that create zeros. So what exactly, let's walk back through this, because you're sort of learning along with me here. Every single thing in here, every string will have an offspring that ends in 1, right? So 0 will have just 0, 1, and 1 will have 0, 1, and 1, or we'll have 1, 0, and 1, 1. So only the offsprings that end, or the items that end in 1 will have offsprings that end in 0, which means that this guy will only have 2 offspring that end in 0, which is equal to the amount of guys in here. And the same is true for this. This guy will only have 3 offspring that end in 0. Because the total amount of things ending in 1 is from the previous are the total amount of offspring that end in 0 for the next. So how do we use this in our formula? Well, we can go a of n is equal to a of n minus 1, which is going to be the odd offspring from a of n minus 1. So if a of n is 4, that a of n minus 1 is going to be 5. So the a of 4 is going to be 5 plus the amount of even offspring that will come from a of n minus 1, which the amount of even offspring is equal to the size of a of n minus 2, because of in here all of these end in 1, which means that there's going to be that number of ones, which means and ones are in the next one. There will be that number of ones in the next one. So if there's 3 ones, ones are the only things that can produce even offspring. So that means that it can only be the 3 from here. So it's going to be 3, because that's n minus 2 is 2, which is 3, so we have 8. So you'll notice that the formula here is just a of n is equal to a of n minus 1 plus a of n minus 2. And that's it. So that's sort of a good idea of the applications of recurrence relations. Now on to complexity. So consider binary search. In a regular search, we know that it's a of n because it's simply the amount of operations is the amount of elements, because let's say we have, or the maximum amount of operations is the amount of elements, because we have a list that goes from 0 to 10, right? So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because again, we have to look through it, because we're assuming that it's worst case scenario with big O notation, right? So that's the span. Now consider binary search, which instead of going through all of the operations that it would take to go through here, it simply cuts in half, cuts off this stuff, and goes 5 to 10. So that's one operation. And then operation 2, it cuts in half, and we go 8 to 10. And then operation 3, we go 9 to 10. Because we're just splitting in half here. And then the final operation, we go 10. And we're either picking 10 or we're saying it's not in the list. So that's 1, 2, 3, 4, 5, 6. 6 is a lot. It's almost half, but it's still a lot. But notice that with 100 items, it is only one more operation, because we go 50, 100, and then we go 75, 100, and then we go I don't really like doing the math in between here because it's obnoxious, but we'll go 82, 100, about. We're really working in approximations here. And then 91, 100. Then we really only have to cut in half a few more times. Let's be really fast here and just say 96, 100, 98, 100, and 99, 100, 100. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And we didn't double our operations. We didn't double the size of our thing. We increased it by a factor of 10, and we only added 3 operations. And that's because binary search is just objectively better. So how do we determine what the complexity is? Well, this is our formula. Because we're cutting, so why is this our formula? It's always, so A of n makes sense. That's just a number of operations, right? number of items total. Number of items cuts in half, which means that's why we're dividing by 2. What the plus 2 is for, I'm not sure. I'm going to assume that it is an initial condition. It's not my business, regardless. This is just the formula we're given for binary search. So we can use what we learned last time when we were looking at recurrence relations, backward substitution. So how do we do that? We go a of n is equal to a of n over 4 plus 2 plus 2. And then we can go a of n is equal to a of n over 8 plus 2 plus 2. And then eventually we'll reach a of n is equal to a of n over n. And then it's plus 2 times something. Usually when it's linear, it's going to be something like 2 times n, right? Or 2 times n minus 1. But you'll notice that the size of the divisor over here is rapidly increasing. Like, it's exponential. It goes 16. So it's going to reach n a lot quicker than it would linearly. So that's going to be 2 log n. And then a of n over n is a of 1, which is just 1 here. We're not told this ahead of time, so you're not expected to derive it. But 2 log n. Simple. So why is it log? Consider this graph, right? On the y-axis we have items or operations, right? Because that's what this is. This is operations. And on the x-axis we have number of stuffs in list. So it goes like this, because it's 2 log plus 1. So let's say 1's right here. And it's probably a steeper curve, but that's irrelevant, right? It's just like curves out. Why does it do this? Well, if you consider binary search, right? The number of operations didn't really increase very much when we went from 10 to 100. It increased by like 3. Even though the number of stuff in list went up by basically 90, right? We went from 10 to 90, and it was like from here to here, right? Like, it was not a big change. But why is that? Well, if we consider it's really just because we're exponentially decreasing the size of the list. So if we look at the inverse of operations, the inverse, which is operations, I'm just going to call it ops, and list size is going to be like this, right? Because the increase in operations requires exponential effort from list size. So, for example, let's say we have let's say we're doing 10 operations, right? That means that our list has to be like 2 to the 10. Or not 2 to the 10. It has to be like 1 plus 2. Well, yeah, it's like 1 plus 2 to the... I actually think it is 1 plus 2 to the 10. Whoopsie. So 2 times 2 is 4. Times 2 is, well, let's just 2 times 2 times 2 times 2 times 2 times 2. This is a lot. You can go 2, 4, 8, 16, 32, 64, 128, 265, 512, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's going to be 1024, right? So it's a big number. I don't think this is exactly accurate, but you'll notice you have to double that, 2048, which, great game by the way, to get anywhere. And then you have to go to like 4096, and it gets really big, like 81, I'm not doing the math here, 60 something, it's probably 90 something, but I don't know. Regardless, it increases exponentially in the amount of stuff you have to have per operation. And that's why log n shows up, because we're doing the inverse of operations of list size for operations. We're doing operations per list size. I don't know if that explanation made any sense, but it at least should have made a little bit. So what does this have to do with complexity? Well, here we have what's called the master theorem, which is a pretentious name, but it almost earns it. So what is the master theorem? Well, it says that f of n is equal to af n over b plus c n to the d. F being an increasing function that satisfies this recurrence relation. In the case that you have this, there's some prerequisites. N needs to equal b to the k. K is a positive integer. A is greater than equal to 1. B is greater than equal. B is greater than 1. Cannot be equal. C and D are real numbers. C greater than 0 and D greater than equal to 0. And how do we use this? Well, it's a little complicated. We should keep it on the page with the letters. So f of n is equal to O and D if A is greater than B to the D. O n D log n if A equals B D O n log B n B log A. Let me see if I can write that better. Log B A if A greater than B. Right, yeah, A is greater than B. So how do we use this? We can use it for our just newly discovered A of n. We're going to write this in as more of a function. A of n is equal to A of n over 2 plus C D D. And so how do we use this? We just look at the values and sort of remember our f, what f looks like. F of n is A f n over b plus c n d, or b d. Since this is all 2, it means that C has to be 2 and D has to be 0. A is 1 and B obviously is going to be 2. So if we look back over here, B to the D is going to be 1 and A is 1. B to the D because D is 0, so it literally does not matter what B is. So that's going to put us right here. So 0 n to the D log n, but again, D is 0, so it's really just O log n. So that's our big O notation. And that's it.